In this video, we're going to look at how to calculate critical regions for a binomial distribution. So let's take an example. So it says a single observation is taken from a binomial distribution that has parameters n equals 6 and a probability which is hypothesized or has a null hypothesis of p equaling 0.35. The observation is used to test the null hypothesis that p is equal to 0.35 against the alternative hypothesis where p is greater than 0.35. Part A, using a 5% level of significance, find the critical region of the test, and Part B states, state the actual significance level of this test. So what we do now is we say it's a one-tail test. We write down the significance level, so alpha is 0.05. And what we want, because it's this greater than, we write it in a special way. So we say that the probability that x is greater than or equal to C2 must be less than or equal to 0.05. So if I was to draw a diagram here, what I'm saying is what we're really interested in is some value, call this C2, because C1 would lie on the left hand side, and we're going to say that that area under the graph, or the sum of all the probabilities, is 0.05. That's what it actually means. When it comes to a two-tail test, we're going to split this in equal sides of the distribution. So that's what we have here. So what we do now is, by default, the binomial distribution is less than or equal to, but this is greater than or equal to, so we do the converse. So we say 1 minus the probability that x is less than or equal to C2 minus 1 is less than or equal to 0.05. So therefore we can say 1 minus 0.05 is less than or equal to probability that x is less than or equal to C2 minus 1. So we get 0.95 is less than or equal to the probability that x is less than or equal to C2 minus 1. So if 0.95 is less than or equal to this probability, we can say, in other words, the probability of x being less than or equal to C2 minus 1 is greater than or equal to 0.95. So don't forget, in our case, we've got the model that x follows the binomial, where n is 6 and p is 0.35. So what we can do, we can go to our binomial tables. So we want to go where n equals 6, so n equals 6 here, p is 0.35, and what we're going to do, we're going to go down this column and find the first value, which is greater than 0.95. So we're in the row of n equals 6, the column of 0.35, and we're going to scroll down, and if we notice, this is the value that we need, and that corresponds to the probability that x is less than or equal to 4. So I'm going to write that down. So you can say from the tables, we can deduce that the probability that x is less than or equal to 4, and we write down its value, is 0.9777. And then now what we're going to say since 0.9777 is strictly greater than 0.95, therefore C2 minus 1 must be equal to 4. So we can say C2 is 4 plus 1, like so. C2 is equal to 5. So therefore we could say, therefore, the critical region required, CR means critical region. A critical region is another way of saying a rejection region. So our critical region is, and we can say x is greater than or equal to 5, like so. So we follow what our alternative says. So if our alternative hypothesis is greater than, then our critical region must be greater than, as we've stated here. So we say that therefore the critical region is x is greater than or equal to 5. Now part B says to state the actual level of significance of the test. So we said in part A that the probability that x is greater than or equal to 5 was our critical region. So we can say CR is that x is greater than or equal to 5. So when you want to work out the actual level of significance, we're going to work out the probability of this actually occurring. So that's the same as 1 minus the probability that x is less than or equal to 4. And we said from our tables that's 0.9777. So we can do 1 minus that on our calculator. So we can say that we're going to get the following here. So we're just going to do 1 minus 0.9777. Perfect. And that gives me 0.0223. 0.0223. And that completes that question. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So we've got that x follows the binomial distribution where n is 10 and the probability is 0.2. Now we need to test the following hypothesis. It's a one-tailed test because it's greater than, so we say one-tailed test. So we can say that what we want is the probability that x is greater than or equal to C2 must be less than or equal to 0.05 because we're testing at the 5% significance level. So as what we showed in the previous example, we do 1 minus the probability that x is less than or equal to C2 minus 1, which is less than or equal to 0.05. Solving this as we did before, we get exactly what we had in the previous example. So we get 0.95 is less than or equal to the probability that x is less than or equal to C2 minus 1. So we can say, in other words, that the probability that x is less than or equal to C2 minus 1 is greater than or equal to 0.95. So we're going to go to our tables here and say, right, so where does that value lie? So remember, in our case, n is 10. So we're going to scroll down to the table where n equals 10, but we need the probability of 0.2, and that's going to be 1, 2, 3, 4, fourth column down in the n equals 10 column, but we need to be greater than 0.95. So the first value greater than 0.95 is here, and that corresponds to the probability that x is less than or equal to 4. So we can write that down. So we can say the probability that x is less than or equal to 4 is equal to the following value, 0.9672. Then we can say 0.9672 is strictly greater than 0.95. Therefore, C2 minus 1 must be equal to 4. C2 is 5. So we can conclude, therefore, the critical region is that x is greater than or equal to 5 in this case. In the next example, here's a case when we deal with a two-tailed test, and it goes back to what I said previously, that we're now going to look at two sides of a distribution, or two tails of the distribution. So we take, for example, in our case 2%, and we divide it by 2, so in total it adds up to 2%. So how does that look like in practice? Well, a random variable x has a binomial distribution that follows the binomial distribution of 40 and p. A single observation is used to test h0 that p equals 0.25 against the alternative hypothesis that p does not equal to 0.25. Using a 2% level of significance, find the critical region of this test. the probability in each tail should be as close as possible to 0.01. So with this, we need to pay heed. And part B, it states write down the actual level of significance of this test. So what we do here is, if we start off by drawing a small diagram and go back to what we said earlier, we want the following scenario. So we take either side of the distribution and we say that at this point we call this critical value C1 and we call this critical value C2. Then what happens? Both of these orange regions must add up to the level of significance, which is 0.02. So we split that on both sides, so we get 0.01. That's why in a two-tailed test we halve the level of significance. So if you notice, if we were to describe this inequality, it would be that the probability that x is less than or equal to C1, that's all of the orange part going all the way up to C1, which is the same as saying the probability that x is less than or equal to C1, must be less than or equal to 0.01. And the other side is the probability that x is greater than or equal to C2, but this is also less than or equal to 0.01. So that's how we form this based on the graph that we've drawn. So if we were to work out the first one, that the probability that x is less than or equal to C1 but is less than or equal to 0.01, notice that in our case x follows the binomial where n is 40 and the probability is 0.25 if the null hypothesis is true. So now if we go to our binomial tables, notice that the probability is 0.25. So let's highlight that. So 0.25 is here and n is 40, which is there. And we want to find the value that's closest to 0.01. Now notice it says as close as possible. It doesn't need to be less than it, as close as possible. Now notice that 0.0047 is closer to 0.01 than 0.0160, because that's actually closer to 0.02. So what we're going to do, we're going to choose this value here, which corresponds to the probability that x is less than or equal to 3. So we can say that the probability, so from our tables, the probability that x is less than or equal to 3 is equal to 0.0047. So what we can say there is the first part of the critical region is that x must be less than or equal to 3, and we can say 0.0047 is closest to 0.01, just to make it clear to the examiner. So the other case is what we did in the previous example, that we're interested in the probability that x is greater than or equal to C2 but less than or equal to 0.01. So that's going to be 1 minus the probability that x is less than or equal to C2 minus 1 is less than or equal to 0.01. So we can say 1 minus 0.01 is less than or equal to the probability that x is less than or equal to C2 minus 1. So here we can say that that's going to be 0.99 is less than or equal to the probability that x is less than or equal to C2 minus 1. So in other words, we can say the probability that x is less than or equal to C2 minus 1 is strictly greater than or equal to 0.99. But remember, the way the question is phrased, it says as close as possible to 0.01. So in our case, we're looking at the probability of being close as possible to 0.99, not strictly greater than, because the way the question in this case has been phrased. So if we go to our table and we can say, right, which value is close as possible to 0.99? It doesn't have to be strictly greater than. So if we scroll down, then we can see that this value 0.9884, which corresponds to the probability that x is less than or equal to 16, is close as possible to 0.99 because it's closer in value than 0.9953. So we're going to say from the tables again, from tables, that the probability that x is less than or equal to 16 is equal to 0.9884. So we know that's the closest possible to 0.99. So I'm going to say closest possible. Closest to 0.99 from the tables. So we can say therefore C2 minus 1 is equal to 16. And therefore we can conclude that C2 is 16 plus 1. C2 is 17. So the next part of the critical region is that x must be greater than or equal to 17. So overall, our critical region is that x is less than or equal to 3, or x is greater than or equal to 17 is our critical region. So if you wanted to work out the actual level of significance, you would say it's the probability that x is less than or equal to 3 plus the probability that x is greater than or equal to 17. So in other words, it's the probability that x is less than or equal to 3 plus 1 minus the probability that x is less than or equal to 16. So in our case, we know what these values are from our tables. We know that the probability that x is less than or equal to 3 is 0.0047. So we can write that down. 0.0047 plus 1 minus the probability that you're less than or equal to 16, in our case is 0.9884. So we write that down, 0.9884. And if we were to type that into our calculator, we get our actual level of significance, which is 0.0047 plus 1 minus 0.9884. And that will give me the required actual level of significance, which is 0.0163. And that completes the question. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So the question states a random variable x has a binomial distribution that x follows the binomial distribution of n being 20 and the hypothesized probability to be 0.40. And we know it's a two-tailed test because p is not equal to 0.4. So we can say it's a two-tailed test, half the level of significance, which is 0.025. And what we want to do is to find the corresponding critical regions. So we can say that the probability that x is less than or equal to C1 is less than or equal to 0.025. And the probability that x is greater than C2 is less than or equal to 0.025. So according to our tables, we can say that we need to be strictly less than or equal to 0.025. And we can see that occurs at this particular point. And that corresponds to the probability that x is less than or equal to 3. So let's write that down. So the probability that x is less than or equal to 3 is equal to 0.0160. Because that value is less than 0.025. So we can write that down, that 0.0160 is strictly less than 0.25. So we can conclude from that point that the critical region is that x is less than or equal to 3. In this case, we're going to do 1 minus the probability that x is less than C2 minus 1 is less than or equal to 0.025. So I'll improve the clarity of that. So 0.025. So we're going to do 1 minus 0.025 is less than or equal to the probability that x is less than or equal to C2 minus 1. So the probability that x is less than or equal to C2 minus 1 is So first we're going to write 0.975 is less than or equal to the probability that x is less than or equal to c2 minus 1. Then we can write the probability that x is less than or equal to c2 minus 1 is greater than or equal to 0.975, like so. Again, we're going to use our tables. So we can say, where does that occur in my table? So I need the first value greater than 0.975, which occurs at this point, which corresponds to 12. So we can say the probability that x is less than or equal to 12. So from tables, the probability that x is less than or equal to 12 gives me a corresponding value of 0.9790. Now 0.9790 is strictly greater than 0.975. Again, improving the clarity here. So therefore we can say C2 minus 1 must be 12. So C2 must be 13. So we add 1 to it. So I'll just write that in. So the critical region is that x must be greater than or equal to 13. So overall, our critical region is as follows: x is less than or equal to 3, or x is greater than or equal to 13. So if we're going to work out the actual level of significance, we're going to work out these probabilities. So let's do that here. All the values that we need are given to us, or we've already written it down. So we know what the probability that x is less than or equal to 3, that's going to be 0.0160. So let's write that down. 0.0160 plus 1 minus the probability that you're less than or equal to 12. So I'm just going to write that here just for the clarity. And then we can say 1 minus the probability that you're less than or equal to 12 is going to be 0.9790. And we can get that result from our calculator. So we can just type that straight in. So 0.0160 plus 1 minus 0.9790. And that will give me the result of 0.037 is the actual level of significance of the test.